Hello everyone, welcome to the course. This will be a two-part TA session on lithography, a specific topic in lithography. I will come to that. And so far in the course, professor would have taught about several micro machine sensors or micro sensors for various different applications. So before we start the topic of lithography or a specific topic what I wanted to say, I will just quickly glance through some of the topics which is a part of course covered, as well as it will be covered in a near future. So as you all know, so these are some of the key topics which has been covered so far. Microfabrication, all of you knows several process flows and all what you have seen for different application. It can be micro heater, it can be IDE, interdigital electrode, it can be some micro cantilevers, it can be any sensors, micro sensors and all this thing. So microfabrication and micro machining have been taught in a greater detail by taking examples of process flow and all. Additionally, one important part of the course is a lab component in which we try to realize or try to show how all this concept work in a real world. So in that also you will be seeing how clean room is, what are the protocols needs to be followed while entering the clean room, gowning, degowning, etc. So all this thing would be covered under the lab component. Moreover, there will be live demonstrations of some of the system which is required or which help in realizing the process called microfabrication. What are those systems and tools? I will come to that. Once you fabricate anything, it is very important to identify whether the thing is correctly fabricated or not. That is where characterization comes into the picture. Because these all devices, as the name suggests, falls under the micro to nano range, which is around 10 power minus 6 to 10 power minus 9 nanometer, and of course it is even smaller than our one hair, okay, and not possible. So it is not kind of clearly by mere visual inspection you cannot see that device. Of course, if there is a device has a dimension of 50 nanometer and 20 nanometer, you won't be able to check whether it is the same dimension has been realized on the substrate or on the sensor when you do that. So to check that, there are several characterization techniques. Now characterization techniques can be test based on the contact or contactless. Most of the contactless techniques are optical techniques, which is like scanning electron microscopy, TEM, all this thing. Equally important as fabrication. In a normal term or in a professional environment, we say development and VNV. Verification and validation. So same holds, same analogy for fabrication or machining with characterization. So this is another important point. Another additional good point is that we will try to cover some of the ongoing translational biomedical research. So that is very important that whatever we are studying, first I have talked about concepts, that is your subject like microfabrication, machining and all. How do we realize that? There comes lab components. These are the system, this is how we realize that. Once you understand the concept, realize it into the real world, and then you are checking, okay, where I can use it. So those are the translational applications which you can use it. So some of the ongoing research or recent trends in this biomedical research will be briefly discussed. Of course, will be providing you a force or guiding you, giving you one objective to go further. Finally, it is up to you. You should be able to swim by yourself. So that's launch pad is being provided, and finally there are some additional skills which is required to make a particular system out of it. So let's deep dive little bit into that. So these are some of the subtopics which will be covered. So as it is mentioned, thin film deposition, patterning, etching will be the part of microfabrication. Now microfabrication is a overall process, consists of several sub processes, one of which would be, first one is whenever you have your system, first you deposit some particular layer known as thin film deposition. It can be done in a physical way, it can be done in a chemical way as well, right? So if it is done in a physical way, it is known as physical vapor deposition. If it is done in a chemical manner, it's called chemical vapor deposition. That is an additive process, which means you are adding something on the top of substrate, a thin film layer. Now how much thickness it should be of that layer and all depends on your final application and decided by the process flow. Okay, so that is like your thin film deposition or additive process. Once you do that, you want a particular design on the top of that. That is where patterning, lithography, photolithography comes into the picture. Exactly what design you want, for which, as it is already discussed, you will be using masks. So mask is where your entire design or thing starts. So using that mask, you will be able to get the same design, or you should be, or you are targeting to get the same design on your wafer. Will we get that? We will see in this class whether we are able to get the same thing, how it happens, how optics play the role. All this thing we'll see into this particular lecture. So that is, patterning is like, a process where you will get your desired design from your mask to your substrate, includes everything. Okay, and ultimately also there is one more process, etching, where you want to selectively etch out a particular portion on your wafer. Okay, so that is where there are also different types of etching. In the contrary to thin film deposition, which is an additive process, etching is a subtractive process, which will remove one particular desired part from your wafer. It can be done through several means. It can be deep reactive ion etching, it can be RIE, all this thing. So that will be covered of course under this course, and also bulk and surface micro machining is also discussed. I've already mentioned the key aspects or key unit process of fabrication, one of which is PVD, physical vapor deposition, chemical vapor deposition and all. In PVD, there are multiple processes, including one of them is thermal evaporation, sputtering and E-beam evaporation. All these systems have been shown. Demonstration would be covered in this course. Okay. Further, I already mentioned characterization. So optical imaging techniques will be there, SEM, CEM, AFM and all this thing. Another important point is we'll be covering tissue engineering, neural systems development and biosensors under the recent trends in this course. Based on different, additionally we'll also try to cover a little bit of ultrasound and how PMUTs and all being developed from fabrication point of view, as well as how it can be useful in clinical world for translational application point of view. Finally, we'll also see three of another important skill which is useful for making any electronic system, one of which is PCB design. So when you have your microchips, let's say you have two microchips, but that two microchips should talk with each other. Okay, output of one microchip should be given to another. How do you do that? Okay, so there will be when you in the design phase, when you are making any microfabricated device, you will put a contact pad or something there, okay, which will help that particular chip or device to communicate with external world. So when that kind of devices are ready, okay, how it will be ready, from how you travel from sand to silicon wafer is one science. Once wafer is ready, how can you make from that wafer to microchip, that is another science. Once chip is designed, how can you use that chip and make a system out of it, that is another science. And of course how you use it. So this is of a system development point of view, this topic is important of PCB design. Once you have a sensor, it will be a very tiny 1 centimeter, 1 centimeter, 2 centimeter based on your application. Once you have your sensor, how you will make sure that a particular sensor will talk with your external world, that is where PCB design or this thing will comes into the picture. Instead of using multiple wires going from one module to another module, it is kind of, there are high chances that you might not get the proper connection or robust interfaces, communication interfaces and all this thing. So how we can mitigate that? By making a small PCB. Now for that There it will be covered in this course how analog electronic modules are designed and customized for your application. Further, once you have that contact pads and all, there is, it should be wire bonded. So all your sensors, that interface should be properly intact. When you want to take any electrical signal from your chip to the outside world, that it should be wire bonded. Also wafer dicing is also another point, because as you know, if you have 4 centimeter wafer, it will have a small different units into that. Same kind of sensor will get replicated 100 times. Then you have to take it out, right? You have to get extract all the instances, all 100 instances. That is where dicing comes into the picture. That you have your wafer, you can cut it. How you can cut it? You should get a desired pattern there, and you should know where in your wafer the designs are. So that's where after characterization you can identify the coordinates and dice the wafer. You will get your multiple microchips. That's the beauty of VLSI, that you will get a small chips are getting smaller and smaller. So in one wafer itself you will get thousands of unit, and hence we are seeing the decrement in terms of price and all this thing. So again, a very important point, wire bonding and PCB design, also 3D printing. When you have anything or you want to make a casing out of it, you want to make a device user friendly, you want to protect a particular unit or particular circuitry or particular sensors from a certain kind of distortions and all this thing, that is where 3D printing comes into the picture. Again, 3D printing itself is a huge area. There are multiple methods, stereo lithography and all these other topics. You can check it and based on that you can make a system. So this is like initial beginning of overall about the course, and it was required for the topic what I am going to teach. So now I will, and also I already mentioned the cover this PVD CVD and all this thing. So now we'll go to the one step further and we'll see what is the most important process in fabrication. So if you are watching this video, I would like to pause the video and think, what is the most important process? Prior to that, you should know which are the processes, which is the most important processes, or what are the processes for fabrication. So I already told that thin film deposition, patterning and etching. Also if you consider the complete cycle from development till validation, there can be multiple more processes as well, right? So this is the question, what are the basic unit processes of fabrication, which I already explained. And there are 4 options you can see here: thin film deposition, patterning, etching and characterization. Okay. So again, one more question here. I have written characterization in a blue letter. So what is the reason behind that? So again, I'll explain. Generally I keep it very interactive, but because it is in online mode, let me explain that these are different processes: thin film deposition, patterning and etching. But characterization is important because there is a reason behind that. Or characterization has a slightly different form of thing, because characterization validates your design or developed design. Okay. However, from this entire fabrication point of view, once you get your desired project or once you get your desired product, desired design, that is optimized thing. Okay. Then after some point, when your process flow is validated, verified, confirmed, you don't have to do characterization. Okay. That is where other 3 processes are important, and out of which one of the most important process or the most important process in fabrication is patterning. Okay. Why patterning? Now we are talking about research. These all are some of the recent trends and all. So why patterning is important? There are reasons behind that. And another thing, as I mentioned, multiple reasons are there. One of which is Moore's law. So if all of you are aware what is Moore's law. So Gordon Moore was a founder of Intel and subsequently Fairchild Semiconductor, if not wrong. So then he has developed, and based on his experience working with semiconductor devices, has come up with his own observation, which is known as Moore's law. I believe it has been followed for last 3 to 4 decades. Okay. What he said is that at every 2 years, the number of units or number of devices you can put it in the same area gets double. Okay, and you can, all of you can observe that if you, now it has become like a history for computers and all, but when first computer was made it was almost like a size of this room. Okay, but ultimately now you see your entire world is in your palm using mobiles, right? So all this thing is like growth in microelectronics, shift in VLSI industries, and there are several companies are, with a great competitors here and there working on that. So that is important. So Moore's law, it was an observation, empirical observation has been followed for last 3 decades. Okay, another, this is like a technical reason why lithography is important, that there is a force behind that and we are able to follow this Moore's law, and you see the rapid growth in electronics industry and all this thing. Apart from that, one another important point is that cost for any company, for any business, it is very important how much you are investing, how much you are getting. In fact, it's the main purpose of any business, small scale, large scale, anything. So lithography, so if you can see the screen, why lithography is the most important unit process, and there are 2 reasons behind that. One is Moore's law, other one is cost. So it has been noticed that almost half of the cost of any microfabrication process is being taken or spent for lithography. One another important point, I mentioned that these all are micro and nano structures, even smaller than our hair size. Minute of difference, okay, can result in defect. Let's say you have a very small defect in your mask, a possible short, you want to make an electrode which should be a different electrode, a possible short in your device, okay, can completely, first of all, defeat the purpose of your development. Now in your mask there is an issue, so it will get reflected 100 times in your wafer, so all your device will be faulty, and as a result of that, what will happen, that your all device will be faulty. Ultimately you have to recall the device. This has happened with microfabrication industries, even a minute and how it can happen. I told you one example of small short, much more examples are there. One of them I'll cover in this class or next class. So then another thing is like cost is very critical. You have to recall all the devices, and there are proofs in the past that company has been completely destroyed because of one recall, semiconductor industries. Okay, hence from companies growth wise also, and companies financially, and also a very critical process, lithography. Okay, how it is being done? So you can see now this left side, this particular thing, it's like a process flow of lithography process paper. Now when you do lithography, you have to make sure that your deposition or thin film deposition is done. Once you do that, you take the wafer, if required you clean it if required, or just to make it ready for the process. Once you do that, you will coat. What you will coat? You will coat photoresist, very important thing. Okay, photoresist has two types of photoresist and all will be covered, positive, negative and all. Mainly properties is it should react to the light differently, and there will be, or ultimately when you have PR and when you expose the light, which you can see here, for optical point of view things will start from mask. Okay, I am just putting here one. It will start from mask. You design your mask and load it. This is loading. Then you have to identify and illuminate a particular source, so which you can see here. And once you illuminate, this is called your this is lens, right? This and this together, there will be multiple lenses. They will be called condenser lens. When I say condenser lens or objective lens, it is not one lens. There is a group of lens strategically placed at a certain distance, so you will get a desired image. Ultimately the entire lithography game is on how light travels from illumination source to your wafer, how you can control that, how precisely you can manage the beams of light and an energy of that. That is entire ball game when it comes to lithography, and that's why it's called photolithography. Very important point. And beneath that, the main principle lies is diffraction, right? In plus 2s we have seen reflection, refraction, diffraction, same phenomena. constructive interference, destructive interference are the main basis why we are getting a desired pattern on the wafer, why we are getting a proper robust microengineering device, microelectronic device, microchips and all the systems. Okay. So coming back to this point, I was talking about that it will start from mask, then it will be kind of you can load the mask, then finally it will get illuminated, and once you illuminated that exposure will reach here and optic things will end here where your PR is coated. Now PR is photoresist, photoresist is getting coated by something called spin coating. If time permit, will show the demonstration. Spin coater coats your photoresist, which is a semi liquid chemical with a finite viscosity. So when you pour it on the wafer and you spin coat it, based on your spin speed it will decide how thick your PR will be coated, and that is already been calculated prior, because your light which is coming from your illumination to your exposure will have a certain energy, so that it can change the solubility or chemical property with when it is exposed, that light will be exposed, the PR's solubility or chemical properties can be changed. So there will be two types of region on the wafer where light is exposed and not exposed. So ultimately it will be mapped into two regions where light is exposed, some solubility X, when other light is not exposed, solubility Y. The difference between that will get exposed to a developer, and then you will get a final pattern. Okay. Also pre-bake, post-bake and all this thing I will cover it. Pre-bake is like a soft bake, post-exposure bake is a hard bake. For each and every PR, the temperatures and timings of this particular pre-bake and post-bake are known. Okay. So now we will go to the next step. So far what you have understood is we will make all these microsensors that are using fabrication. In that fabrication, what is important process? We have seen lithography. Why it is important? We have seen. Let's even go deeper. What is most important in lithography? Okay. Now all of you know that what are the processes in lithography, right? First is to wafer preparation, or that you get the wafer, then coating, pre-bake. I'll just consider the entire step as fourth, and is expose, post-exposure bake, development and metrology, right? This metrology is nothing but characterization, same thing. Okay, what I have explained. So these are like 7 steps. So again I want you to pause the video and think that which of this is the most important step. Okay. Okay, so now as you have thought about it, I would say that exposure is the most important step. Now I already earlier also I asked that when you select a particular thing, okay, out of this 4 thing, 5 thing, which is better, okay, you should know why that particular thing is better. As a researcher or as a good person also with a proper rationale, you should have some idea that why you are going for one particular thing. So you see that I have mentioned that optics, imaging and exposure are the most important point. Again the question is why optics is the most important part of lithography. So there are 2 points behind that. One, again, that's Moore's law, what I have already explained. You can see the screen here. One is Moore's law. Second one, the more important point is it defines your CD. Okay. CD is nothing but your critical, you can see it in the screen, critical dimension. Okay. The smallest possible dimension on your device. Let's say, and some of you might have heard the term pitch. For semiconductor pitch, it is around 45 nanometer, 10 nanometer, 5 nanometer. What is this? All this. Those are your critical dimensions. So minimum dimension is that much. Okay. So again, very important point in lithography. What is important process? You can see it in this blue color highlighted part. It includes everything. So does that mean other processes are not important? No, they are important. They are very important. Any one of this process fails or any one of this process is not optimized, you will not get the desired result. Okay. But when I talk about coating, when I talk about pre-bake, when I talk about post-exposure bake, when I talk about development, this all sub processes have been optimized or saturated when it comes to improvement. However, there is still some magic left in exposure or optics which can help you or which can still take this bandwagon of miniaturization in microelectronics further. Okay. So now we will see prior to moving to optics, a quick MCQ or some small test. This would be, or I believe professor would have covered lithography. So, I have a question that which kind of lithography is. It is always important to know where do we stand today, but how we approach from that point. In research terminology, it is called reinventing the wheel, right. So, let us see which kind of printing is that. Now it is already clear. Again, stop it and think about this particular thing, what kind of lithography. This is a projection printing. Now we know why it is projection printing, based on the projections of light from through lens, through mask and coming to your device and all clear. What are the other two types of printing? Very important. One is contact printing, other is proximity printing. So in contact printing, it is very simple thing that you have things on your mask, you know put that mask on the device and you will get that kind of thing. Okay. So that is nothing but your contact printing. Now that had some limit. Let us say if I talk about contact printing, this is my mask, this is my device, I will just put it like this. This would be my final image would be created here. Now the thing is it limits number of times you can do this kind of exposure or contact to get the device, and hence you cannot get multiple products or multiple devices with one mask. So that limits, you have to keep on generating mask also, keep on generating device also. So that limited kind of, then we further move to proximity printing, where they have to keep it at a finite distance between your mask and this thing. Okay. However, that proximity printing worked till 4 micrometer. Now currently all of you, I would like to encourage all of you to check, all of you are very smart people with smartphones, right. So just check what is the technology used in that particular smartphone. It would be few nanometers. So current current devices demand for a really low pitch, right, around nanometer scale, and hence then from there finally shifted for proximity printing, they have a limitation to projection printing. Okay. Now we will see today's thing. Generally I keep title slide first, but in this I have kept it here because if I start from here and if I ask which is important process, all of you will say lithography. In that if I say what is important sub process, all of you might say lithography optics. So whenever I teach this, I keep this slide in between. Okay. So this is our today's topic, and I am Rathin Joshi, recently graduated from Indian Institute of Science. So we will see directly what is the most important factor in lithography, that is called as resolution. All the microelectronics companies, all the electronic front runners, you can say Apple, Intel, all these companies, okay, their entire work or how many whatever they are doing, finally their evaluation parameter is resolution. How much smaller dimensions you can successfully reproduce on your wafer. Okay. That is their final metric. Like if you study anything in this course, your final evaluation could be the skills what you have learned and also little bit of the marks you get, right. So in this lithography or electronics company, resolution is the important thing. Let us see what is that. So Rayleigh has come up with an empirical formula. So it is not like where is the derivation of this formula, it is an empirical formula, and that is true only for projection or diffraction based lithography what we are considering it right now. Okay. He has come up with a formula that resolution R is equal to k lambda by Na. Okay. Whereas k is your system parameter. What is that? We will come to that. It depends on how you are illuminating the source and all. I have shown earlier here we are illuminating, right. So how you are illuminating this source, is it like this direction or it is inclined or it is this side, we can control that. So based on that it will decide what is your k value. Again when I will come to that, I will show you that particular thing. That is your system parameter. Lambda is your wavelength, right. Of course whatever things you are doing, you are already identifying that what is your optical source you are using. It can be laser, it can be excimer laser, it can be any other source. I'll show you the spectra in a short while, that what are the lasers and all being used, what nanometer and all. So that wavelength matters a lot. that also you know this all are lights and all are EM waves. So you check the electrical property and magnetic property perpendicular to it, and then they have some energy, and check what is EM waves energy formula, how it is connected with wavelength, and all these studies have already been done. Okay, that is your wavelength. And finally it is numerical aperture. Numerical aperture is a property of a lens to acquire light. I will come to that. This is the most simplest yet most informative kind of illustration of your diffraction limited lithography. Okay. So you see here there is a source here, and before I explain anything I want to tell you this is the thing. See, this is source, this is condenser lens, okay, this is mask, this is objective lens, and this is wafer. The same thing what you can see in this fashion here, right, rotating it and showing it like this. So if you can see, now you see this thing, it is like this. Let us rotate it and see it like this. It starts from source to wafer, top down. Now we will see from this side, okay, this is the source and final wafer here. Okay. So let us see, it would be very easy now to understand. You see source is here, condenser lens, mask, objective lens, and wafer. For the sake of simplicity, only one condenser lens and only one objective lens is shown to understand make you people understand the principle. Okay. So this source, it is like kind of illuminated. As a result of that, at a mask, when mask is there, this blue color is your mask. Okay, this blue color part what I am currently making red is the mask, and the other one is just a load, or when you can put the mask, it will be opaque, it will allow all lights to pass through that, but mask will not allow. Mask only a certain portion when you can it also depends on which kind of mask you are using, of course bright field or dark field, but let us say some portion it will pass through the and some portion it will get stopped by mask, and that is what we want. So your design of the mask will get reflected on wafer. Okay. And then you see that it gets diffracted here. Okay. Please check what is the kind of fundamentals of diffraction and all. It is getting diffracted here. Let us say it is getting diffracted at theta, so it will reach to this point here, and then from here it will come here. This will go here, it will come here. What if some light gets diffracted from here only? Let us say what if some light get diffracted at some more angle alpha, and it will not get acquired by the lens. So this is where your numerical aperture of lens comes into the picture. Ability of your lens to acquire a certain amount of light. Okay. Higher it is, you will get better picture. Okay. So it is like and you can see the formula also. If numerical aperture is higher, your resolution is less. Another point is resolution less is better or high is better. Always as much less resolution as possible is good for your particular thing. So that is where your resolution comes into picture. Again, depth of focus, another important optical parameter. I told you this all depends on your interference and all this thing. That depends on your path delay or path difference between two particular beams. That get decided how much separated these two things are, distance between mask and objective lens, and also condenser and mask. So how much kind of movement you can allow, tolerance here, that is what is known as your depth of focus. Okay. So now another quick observation here is, if numerical aperture is higher it is good, but then when numerical aperture is higher it will lower down your resolution, but it will keep the DOF, depth of focus, even less. So the problem is you have to very precisely locate the objective lens, which is again a difficult thing. I will come how big this system and all, I will come to that, but however this is your depth of focus in brief. And finally we will see how can we improve, because as I mentioned the entire game is on resolution. How we can improve that? Forget about microfabrication, forget about lithography, forget about everything. This is a mathematical formula, think like that. How you can decrease R? As simple as that. You can decrease K, you can decrease wavelength lambda, or you can increase Na, as simple as that. Each thing corresponds to one particular, this all four things are known as R, E, T, very important. RET is resolution enhancement techniques. Okay, I will cover each of them in the next class. One is phase shifting mask, where you are mask is there. Generally mask only alters your amplitude or gets it diffracted. If you can change the phase also, it will have some different in terms of interference happening at this particular point and this particular point. As a result, you will get a desired pattern. I will come to that, do not worry about that. Another point is off axis illumination. Currently if you see, this is normally, this all waveforms is normal to the mask located. So this is a normal incidence, but what if I will do some magic here and instead of this it will be like this, okay, that will affect my k parameter. I will write it here. So if there is a normal incidence, okay, k value is 0.5. Now this is prune, and if it is off axis, okay, another name of that is oblique, okay, then your k value is 0.25. If I go one step ahead in terms of optical interference and all, when it is my normal imaging, okay, or normal incidence, okay, it will be 3 beam imaging. Your final thing gets decided by 3 beams, whereas in this it is 2 beam. Again we will come to that, what is 3 beam and 2 beam. Further there is another point. So we have seen phase shifting mask, we have seen off axis, now we will see immersion lithography. When you pour, you see this objective lens and wafer, in between you change the medium. Generally when it is not specified, it is air, but if you change it by water, okay, it will affect, of course you know that numeric this Na depends on your refractive index, and water's refractive index is bigger than air. So when you change it to water, you will get some higher Na, and as a result get a better resolution. So that is your immersion lithography. And finally lowering wavelength, that is also important point, because as simple as you can see here, but when you lower the wavelength you have to take care of so many other things, because when you lower the wavelength for any EM wave, it will increase the energy. That should not be that much that it will affect or gets reacted by anything in between medium and all these things. So several other parameters, I will not go into the detail. So that lowering wavelength is also equally important thing, okay. So now we will quickly see some of the examples. Examples are very easy and might be helpful for you in some assignments and all, or some exam at some point of time, but the most important part is you should know what is the physical inference out of it. So first numerical says that a PR gives a final resist thickness of 320 nanometer when spun at 2800 rpm. What should be the spin speed if you want 280 nanometer of coating? So first thing is you should know the relationship between resist thickness and spin speed. Now it is very evident that if you spin it at a higher speed, you will get a thinner final thickness would be less. If you spin it at a very low speed, you will get a really thick layer of PR, okay. But how much thick you will get or how much thin you will get based on your spin speed, we will see that in this example. So main thing is to realize physically that how it is related. Second thing is to know the relationship. So now if you see, this is the formula. Out of 4 parameters, 3 things have been given. Your thickness first, your 2 speeds, spin speed is shown in omega, and it is inversely proportional to the square root of spin speed, okay. Any of you out of 4, 3 values are given. Even a 10 standard student can put the value and calculate it. But where you stands apart is you should understand what is the physical interference. We are talking about PR coating. PR coating is a sub process of lithography, which is a sub process of microfabrication, and that is why we are kind of checking it. Another important point, yeah, you know that we are talking about this thing, same thing what I have told. Another important thing is you should check is that, see, earlier your thickness was 320 nanometer, okay. Now you want it 280 nanometer. So you have reduced it by at least some 10 to 15%, but you need to increase your spin speed by almost 20 to 25%. So how it is correlated, and spinning it at a higher and higher speed has its own consequences, okay. Sometimes when you spin very high, you will not get the desired thing, or conformal thickness of PR. It might be more kind of localized or more formed in the edge bits or edge, and that is where edge bit removal is another important part of lithography. So that is also important thing, and I would like strongly encourage you to check what is edge bit removal for PR coating, very important point for any lithography process. Another example, if you see, what is the ratio of minimum feature size achieved using G line and H line wavelengths of a mercury arc lamp. Now mercury arc lamp is used as an illumination source for a long time. Consider that the same photolithography system is being used. So your lenses and everything is same, the way you are illuminating your lenses is same, which is in other words saying that your numerical aperture and K remains the same. Now this is to just to give you people an idea what is G line and I line. This is some energy spectra when you are doing some experiment, where it peaks it will have a highest energy, which will help us to use it in lithography as a illumination source. So now in this particular problem statement it is written G line and H line. So you can find G line here, H line here. Now people have used G line, H line, I line, krypton fluoride, argon fluoride, fluorine, argon and some unknown peak, and currently people are using this thing 13.5 nanometer called extreme UV. This what we are talking more or less falls into UV range. Okay, this and all apart from this example, these are our important information. Okay, this is what you can see in visible spectrum. Okay, so now let us see what is the ratio of resolution is asked, and again how to improve resolution and all you already know. Resolution definition, Rayleigh's resolution you already know. Now for any system, same system beam is used, so you should always read what is given in the problem statement. Same photolithography system is being used, hence we can consider numerical aperture and K value constant. Okay, so then finally you just put the values, take the ratio and you will get an value. That's it, as simple as that. Okay, one last example for today's, that is in an optical lithography system a krypton fluoride source is used with 2 beam imaging. Now already earlier explained, 2 beam means K value is 0.25. Okay, so 2 beam means K value 0.25. Consider numerical aperture already provided, compute the resolution in this case. Now what you need okay, wavelength also is given, krypton fluoride source, you got K, you got lambda, you got Na, just put the value you will get some nanometers. So this is around 45.92 nanometer is your resolution. What is resolution? Smallest half pitch which you can successfully produce. If this is half pitch, now you read the next part. Will the given parameters fulfill the requirement if process requires 60 nanometer pitch? Now this is your smallest half pitch. So what is your full pitch? It is around 91.84. So it is almost 92. Always remember, you will never get the ideal or calculated value when you do the fabrication process. It will be always little bit more. So consider 92 nanometer is your final outcome. So will the given parameters fulfill the requirement if a process requires 60 nanometer? Now based on the scenario or lithography system details have been provided, it is can successfully produce 92 nanometer pitch. You want to go even lesser than that. Can you do that in this system? No. Then how do we do that? So with this system or given scenario, we cannot print 60 nanometers. There are some more magic, some more alternative, some more resolution enhancement technique you have to perform. Okay, so that is what we will see. To improve this thing, resolution and all, it is mentioned that RETs will used. This is slightly quick point which I want to put, because all of you know what is photolithography and all. Very important to know what are the actual values. So this is for SU8. SU8 is negative photoresist, frequently used. You will never get a complete kind of materials used to make a SU8 photoresist. That is something, a trade secret which PR companies keep. They will give some name like AZ222, something like that. And you see SU8 only, there are 5 variants. Based on the number of solid used and viscosity, you will get different variants of this SU8 photoresist. Each variant has its own application. You see when it is spun, okay, how their film thickness is getting decreased. So for 2 different regions they have given it like that. Also at what thickness you want and what kind of exposure should be done from illumination. Important point, what is soft bake time, hard bake time and development time, and how much dosage you should give. All these things are important parameters when it comes to realizing fabrication process, and this is available in the, if you search anywhere SU8 photoresist PZF, you will get it. So just not only understand what is given in the as a concept, also understand how actually in real world it matters. Okay, so again this is like a overall idea. You see from 1975 to 2001 how resolution has improved, and beyond that which are the important parameter. I told you that we can lower the lambda, right? They have lowered it from 436 to 193. Currently if I can put one more line here, 2024 and all, people are even gone beyond that 13.5, but that is a different process, EUV. Okay, so you can see how much it has decreased. It has decreased 2.3x if I consider only these two values, 1975 2010. Numerical aperture has significantly improved from 0.16 to 1.35, that is 8.4x, and your k parameter has been changed from 1 to 0.25, so that is around 3.5 to 4x increment. Overall whatever you are getting, around 2.7 micrometer has been now reduced to 40 nanometer, okay, 68x. So this is like a good realization that because of which particular driving factor we are able to get this kind of thing. How much further smaller we can get, that you have to decide, and you have to kind of check how do we do that. See, consider this thing, one of the optimal source, whatever we have talked about, all the sources I have given you energy spectra, consider that. Consider oblique illumination, you should know what is k value if it is oblique illumination. Also consider the biggest possible numerical aperture which you can get, consider 1.35 for now. Put the values, identify what smallest pitch you can get. Okay. On the contrary, whatever values you get, foundries have successfully fabricated 2 nanometer resolution. So let us say with this you are getting some, pause the video and check, let us say you are getting 50 nanometer, I am just assuming, okay, I will ask next time what the value you got. So how from 50 nanometer they have dived to 2 nanometer, you see this 50 nanometer to 2 nanometer, significantly different, right? How do they do that, right? That is something we will see in the next class. These are some of the initial recently last 3-4 years progress. You see IBM has successfully come up with 2 nanometer I mentioned. Then TSMC is in Taiwan, that is a really important workforce when it comes to Taiwan, and that is why Taiwan has a really big geopolitical importance, and so many things are happening. So this TSMC you see 1.4 nanometer is what they have claimed. This is again before 2 years. So if we talk current picture, it might be even less, right? So these are like some of the improvements in the recent world. How do they do that? So we will see that in the next class with some of the resolution improvement techniques. If you have any questions, feel free to connect with us, would be very happy to answer it. And just briefly in a nutshell what we have kind of gone through today, how microfabrication and related things will be covered in the course, what is microfabrication's sub-processes, unit processes rather, which is the most important unit processes, in that important unit process what are the sub-processes, in that which was the important part which is lithography optics, and then in that lithography optics we have seen how resolution can be approximated and some numericals, and we have also seen what are the real values about photoresist and some of the recent advancements in miniaturization and all this thing. So again we will see the next class how we can go even further and go till less than 10 nanometer. We will see in the next class. Till then all of you go through this. Some point I said you try to explore by your own, please do that. If you have any question something, feel free to connect with us. I will see you in the next class. Take care, bye.